video of this review. What's this? Triangle. Good. There's some really beginning parts of review. If I add that onto it, what does that do? What kind of triangle is that? Right triangle. What angle does that little square mean? 90 degrees. If I put some sides on here, can you tell me the other side? And we got 5. Okay, good. So we remember doing a squared plus b squared equals c squared. 3 squared would be 9, 4 squared would be 16. Add them together, you get 25, so the other side is 5. Okay, let's do some more mental math. Let's change up the numbers here. Let's say we do 8 there. What's the other side? And if you left that as a square root, so 8.54 is the decimal, but we're going to leave this as an exact answer, and so 73. And again, you just did a squared plus b squared equals c squared, right? How about if I gave you this side, took this one away, and I said this side is 6, what's the other side? And we'll leave it as a square root. Oh, here, we'll get, you know what? We're going to be doing lots of this mental math. I've got scrap paper. Take 2 or 3 pages and pass it around. You can scribble some stuff down. You can figure it out. Square root of 27. And again, that's an exact answer. If you go to a decimal place, then it's not an exact answer. And what's another way that I could write the square root of 27 if I wanted to simplify it, but not leave it as a decimal? Close, very close. We do want to write it as a number square root of something. Yes. How do we figure out what those numbers are? We have to break up 27. And breaking it up with 25 and 2 adds it. But we want to break it up with multiplying. What times what is 27? 9 times 3. And when we're multiplying square roots, this is the same as square root of 9 times the square root of 3. And we'll get 3 root 3. So square root of 27 is equal to 3 root 3. And that's something you've done from before. So we can take our square roots and simplify them. A squared plus b squared equals c squared. When did you start doing that? Long time ago. That was like middle school they start doing that. Okay, good. We do tons of a squared plus b squared equals c squared in grade 12 as well. Now, if I took this and I said, what's that angle? We'll do this first as a grade 10 question. If we do this as a grade 10 question, I'll let you use your calculators. If we do it as a grade 11 and a 12 question, this one would be without a calculator. But we'll do it as a grade 10 question. Take out your calculators. You're going to need them for this review. I've got a few extra here if there's people that do not have a calculator. Anybody get a value for that theta? What'd you get? Not yet. 30 degrees. Beautiful. 30 degrees. What did you do to get that 30 degrees? Okay, so you did sine inverse. See that minus 1? And we're talking about inverse notation. Sine inverse of 3 over 6 in your calculator, and it gave you 30 degrees. Now this is based on, we use sine and 3 and 6. How come? Because you know that sine is the opposite of the hypotenuse. Maybe some of you would even set it up first by writing that. I know that sine of that angle is the opposite side divided by the hypotenuse, and I get 3 over 6. How come in grade 11 this would have been a non-calculator one? Do you remember those values you memorized in grade 11? No. We have to memorize them again in grade 12, so if you don't remember them, that's perfect. We get to do it again. One of the ones you remembered, 3 over 6, reduces to 1 over 2. And 1 over 2 was one of those values that you memorized that went with 30 degrees. So 30, 45, and 60 were probably the values that maybe now ring a bell that, yeah, we tried to remember those, and I don't know them anymore. It's okay. We'll get to do them again. So if I give you a different triangle, and it's right angle triangle, what would you use here? What would the angle theta be? Oh, by the way, on that last one with 30 degrees, did anybody get a different answer, like a 0.6 or a 0.7 on their calculator, other than 30 degrees? Was anybody's calculator not in a degree mode? So if it's not in degree mode, you might get a different answer. And if it wasn't matching up with 30 degrees, that might have been what was happening. Now this one with degrees, what did you get for degrees here? 59 degrees rounded, okay. And did you use sine? No, how come? You didn't have the hypotenuse. We had the opposite side and the adjacent side. So which one did you use? Tan. And the opposite over adjacent, so to find theta, we would do in our calculator the inverse of 5 over 3. Perfect. This is grade 10 trig. Lots of triangles, figuring things out on triangles, SOHCAHTOA, finding out those ratios, and working with them. Now what happened in grade 11 is, in grade 11 we started to go something like this. Cos of x is equal to 0.75. What's x? The triangle disappeared. We just have an idea. How do we figure out what x is? Oh, and in grade 11, they would have also said that x is somewhere between, and they'll give you some sort of domain to work with. We want to look between 0 and 360 degrees. So what do we get for x? 41.4. Perfect. And if you type that in, if you type cos of 41.4, you get close to 0.75 because that's rounded. How did we do that? You probably went cos inverse just like you did before. But now, if I say to you, hey, I would like you to type this into your calculator. Cos of 318.5904. What do you get? Or what do you get really close to? The same thing. And, well, Isn't that a right answer as well? When we came up with 41.4, it's one of the answers, but now there's another answer as well. That 318.59 is another answer that works. Oh my goodness, how many answers are there going to be? Is there more than this? Is this all there is? How do we figure this out? What's happening? Well, to build on this, we need to review a few other things that we learned in grade 11. One of them is the cast rule. How many people have never seen cast or the words? So everybody here is aware of that. Okay, but we're going to review it anyways. I need someone to pick a random angle in quadrant 1. And just to label things here, this is quadrant 1. This is called quadrant 2, quadrant 3, quadrant 4. And as far as angles go, starts at 0. This would be 90 degrees here. We're going around 180 degrees here, 270 degrees here, and all the way around is 360 degrees. So quadrant 1 is from 0 to 90 degrees. Give me a random angle in quadrant 1. 45. Yeah, I kind of like 45. I want to. 53 seems more random. 45 kind of sounds like right between 0 and 53. I like 53. Okay, so we're going to type into our calculators, find out what sine of 53 degrees is, what cos of 53 degrees is, and what tan of 53 degrees is. So we'll do that quickly, write them down. And when we put them in, all three of them give us positive numbers. Sine is 0.7986. Cos is 0.6018. And tan is 1.327. Perfect. And they're all positive. That's what this A stands for here. That A stands for all four of them. Four of them? Wait a minute. All three of them are positive. Whew. By the end of this unit, we'll say all six of them, but we're not there yet. So far, just 3. Oh no. All 3 of them are positive in that quadrant. And when we go to quadrant 2, so you picked a random one in quadrant 2, I'm going to pick an angle in quadrant 2. I'm going to choose 127 degrees. And when we plug these into our calculator, and don't do it yet, when we plug these into our calculator, some of the answers will be positive and some of them will be negative. Which ones will be positive and which ones will be negative? This one will be positive. And those ones will be negative. That's what our cast rule tells us. Now you've probably memorized your cast rule. This unit will help explain why they're positive and negative in that, and I might even get to that in this review today. But for right now, you're right. Those are positive, those are negative. Good. Now I'm going to tell you that based on what you learned in grade 11, without your calculator, you should be able to, at this moment, tell me to 3 decimal places what tan of 127 degrees is. The same as the first one, but it's negative this time, 1.327. And it just so happens that cos is the same as that one, And sine is the same as that one. Why? Why do we know that? Is my QR. You forget what it's called. Okay. You're right. It's my something R. And that R stands for something. Reference angle. So we're going to also have to review this, because this is the foundation of what we're doing right now. Reference angle is a huge thing in trigonometry that we've learned already in grade 11, and we build upon it on grade 12. In fact, we have to know it so well, because when we build upon things, it needs to be a strong, strong foundation. So let's just do quadrant 3 and quadrant 4 and see if you can figure out what angles I'm going to pick. I'm going to go to quadrant 3 now. And I'm going to pick angles. Can you guess what angle I'm going to write when I go to quadrant 3? $233. And when I go to quadrant 3, which ones are positive and which ones are negative? Tan is the one that's going to be positive. Sine and cos are going to be negative. And when we type these ones in, sure enough, sine stayed the same. Cos stayed the same. And tan stayed the same. So how did I think of that 233 degrees? Where did that number come from? And when I go to quadrant 4, what number am I going to put now in quadrant 4? $307. And sure enough, the values are going to be the same again. Which ones are positive, which ones are negative? Cosine is the one that's going to be positive. Sine and tan are going to be negative. Oops. And we have the same numbers again. And the key to this is something called a reference angle. Why do these numbers stay the same? What does this mean? How is it that if they have the same reference angle, that their angles do stay the same? Well, let's think about that. If I draw 53 degrees, well, I'll do the one in quadrant 2. If I draw 127 degrees in quadrant 2, when we're labeling that 127 degrees, that starts at the positive x-axis, and we would say that this is an angle in standard position. Any angle that starts on the positive x-axis and goes to an end somewhere, we call the place where an angle ends the terminal arm of the angle. So an angle starts on the positive x-axis, it ends at its terminal arm. That's an angle in standard position. For this angle right here, 53 degrees is your reference angle. Your reference angle is your positive angle to the nearest x-axis. But that doesn't explain why is it that I got the same answers for tan of 127 than I get when I do tan of 53. Why does that happen? Why are reference angles so important? Well, the reasoning is if I take 127 degrees, and on here I take a point and I draw a line straight down, I make a right angle triangle. And that right angle triangle has 53 degrees in it. That is the same right angle triangle, or similar to if I took 53 degrees in quadrant 1 here and I drew that same triangle, right angle triangle, those two triangles are identical. And the definition of what is sine of 127 degrees is still based on your grade 10 math, that sine is the opposite over hypotenuse. So when I look at 127, well, I'm actually looking at this triangle here, and I'm taking this opposite side over this hypotenuse, which is exactly the same as this opposite side over this hypotenuse over here. And it actually doesn't matter with triangles whether they're identical or just similar. Like I could have made it a bigger triangle here, and it would be the same thing. Are you aware of that idea? So if I drew my 53 degrees here, if I drew my 53 degrees and we figured out what sine of 53 degrees was 0.7986, so I could say since sine of 53 degrees is equal to 0.7986, I could make this side 0.7986 and this side 1. And if I took this triangle and I made it bigger, and I kept this at 53 degrees, and I made it bigger so that, let's see, this looks like, now it looks like this side is 2. How big is this side? It's going to double as well. So that would be 1.2, close to 1.6. There we go. It's going to be double. And that's what's powerful about triangles, that if you keep the angle the same, everything is in proportion. And so when your calculator tells you sine of 53 degrees is 0.7986, it doesn't matter how big or how small that triangle is, the opposite over the hypotenuse will always divide to get you this. So if I take 1.6 divided by 2, I get 0.8 because I rounded. But that is the same ratio as before. It doesn't matter how big or how small you draw that triangle, those ratios are always the same. And your calculator has all those ratios built into it. You have a triangle, you want to solve for something. If we go back to the questions that we were solving to begin with, I could add a grade 10 triangle question. Put 27 degrees there. Put x there, put 5 there. What's x? How do you solve for that? You'd have to use your calculator. How would you set it up? Would you use sine, cos, or tan? 2.3? It looks like it would be mighty close to that. Be rounded, right? Yeah. So what do? Well, we would use sine here because we've got an angle, we have an opposite, and a hypotenuse. Your calculator has built into it what the proper ratio of sine of 27 is. When you type sine of 27 in, it tells you the ratio. And we want that ratio to be equal to the opposite over the hypotenuse. So in this case, now you use your algebra skills. If I want to get x by itself, I'd multiply both sides by 5. And when I round, I get x is approximately 2.3. But that's your idea. The idea here, so 90 degrees, that all of your sine, cos, and tan ratios are built into your calculator. It doesn't matter how big or small, that ratio stays the same. That's what trigonometry is all about. But now we build upon that. This was grade 10 with triangles. Grade 11, we take the triangle away and just tell you the ratio was 0.75. What's the angle? And we found out that the angle is not just 41.4. It also included 318. Why did it include that other one? Well, because of our idea of reference angles and cast. That for all these different angles, we get the ratios to be the same. So if I want a ratio of 0.75, my cast rule tells me it needs to be in quadrant 1 or quadrant 4, because that's where cos is positive. So in quadrant 1 it was 41.4, in quadrant 4 it was 318.6. Why does this happen? Because when you draw an angle, you can always draw a right-angled triangle using your reference angle. And so every set of angles that have the same reference angle will have the same answer. Just what will be different is some answers will be positive and some answers will be negative. So now I'll do another grade 11 question here. Another grade 11 question that you would have solved. We haven't used cos for a bit, so let's take cos of x is equal to negative 0.28, not theta, where 0 is less than x is less than 360 degrees. So this is a grade 11 question that you would have had. And I'm going to show you the work that you would have done in grade 11, the least amount of work that you could have done in grade 11 to show the right answer. Okay? So when you were dealing with this question in grade 11, the first thing you would have solved for is your reference angle. This is where the little r comes into place. We take whatever angle we have, in this case it's x, we write a little r to say we're finding the reference angle for x. And we figure that out by doing cos inverse of 0.28. Reference angles are always positive. Type that into our calculator. Cos inverse 0.28, and we get 73.7 degrees. We then can say our answers are 253.7. I'll write that one second. first one was 106.3 degrees. Okay. So this is the least amount of work that you would have needed to show. That's not what I wanted to do. That's the least amount of work that you would have needed to show in grade 11 to get the right answer. And you might have got your trig answers right in grade 11.